6. Operating system design and implementation. The first problem in designing a system is to define goals and specifications. At the highest level, the design of the system will be affected by the choice of hardware and the type of system: batch, time-sharing, single-user, multi-user, distributed, real-time, or general purpose. Beyond this highest level, the requirements may be much harder to specify. The requirements can be divided into two basic groups: user goals and system goals. From user goals, user wants certain obvious properties in a system. The system should be convenient to use, easy to learn and to use, reliable, safe, and fast. Of course, these specifications are not particularly useful in the system design, since there is no general agreement on how to achieve them. And from the system goal, operating system should be easy to design and easy to design, implement and maintain, as well as flexible, reliable, error-free, and efficient. So let's look at mechanisms and policies. One important principle is the separation of policy from mechanism. Mechanisms determine how to do something. Policies determine what will be done. For example, the timer construct is a mechanism for ensuring CPU protection. But deciding how long the timer is to be set for a particular user is a policy decision. The separation of policy and mechanism is important for flexibility. Policies are likely to change across places or over time. In the worst case, each change in policy would require a change in the underlying mechanism. A general mechanism insensitive to changes in policy would be more desirable. A change in policy would then require redefinition of only certain parameters of the system. For instance, consider a mechanism for giving priority to certain types of programs over others. If the mechanism is properly separated from policy, it can be used either to support a policy decision that I/O-intensive programs should have priority over CPU-intensive ones, or to support the opposite policy. Microkernel-based operating systems take the separation of mechanism and policy to one extreme by implementing a basic set of primitive building blocks. These blocks are almost policy-free, allowing more advanced mechanisms and policies to be added via user-created kernel modules or user programs themselves. As an example, consider the history of Unix. At first, it had a time-sharing scheduler. In the latest version of Solaris, scheduling is controlled by loadable tables. Depending on the table currently loaded, the system can be time-sharing, batch processing, real-time, file share, or any combination. At the other extreme is a system such as Windows, in which both mechanism and policy are encoded in the system to enforce a global look and feel. All applications have similar interfaces, because the interface itself is built into the kernel and the system libraries. The Mac OS X operating system has similar functionality. Policy decisions are important for all resource allocation. Whenever it is necessary to decide whether or not to allocate a resource, a policy decision must be made. Whenever the question is how rather than what, it is a mechanism that must be determined. Implementation. Once our operating system is designed, it must be implemented. Because operating systems are collections of many programs written by many people over a long period of time, it is difficult to make general statements about how they are implemented. Each operating system was written in assembly language. Early operating systems were written in assembly language. Now, although some operating systems are still written in assembly language, most are written in a higher level language, such as C, or even high level language, such as C++. Actually, an operating system can be written in more than one language. The lowest levels of the kernel might be assembly language. Higher level routines might be in C, and the system programs might be in C or C++. The advantages of using a higher level language, or at least a systems implementation language for implementing operating systems, are the same as those gained when the language is used for an application programs. The code can be written faster, is more compact, and is easier to understand and debug. In addition, improvements in compiler technology will improve the generated code for the entire operating system by simple recompilation. Finally, an operating system is far easier to port, to move to some other hardware if it is written in a higher level language. The only possible disadvantages of implementing an operating system in a higher level language are reduced speed and increased storage requirements. This, however, is no longer a major issue in today's systems. Although an expert assembly language programmer can produce efficient small routines for large programs, a modern compiler can perform complex analysis and apply sophisticated optimizations that produce excellent code. Modern processors have deep pipelining and multiple functional units that can handle the details of complex dependencies much more easily than can the human mind. Major performance improvements in operating systems are more likely to be the result of better data structures and algorithms than of excellent assembly language code.